Welcome to another coding tutorial, and in today's video, I'm going to show you how to create this generative art sketch inspired by this fascinating piece of early algorithmic drawing. This sketch is inspired by the book called DESSIN Géométriques et Artistiques avec votre micro-ordinateur. I took French in high school, but it's been a while. Written in 1985 by the French mathematician Jean-Paul Delahaye. The original programs were written in Microsoft Basic, run on a Canon X07 computer, and plotted on a Canon X710 printer. And I discovered this book through an amazing project by generative artist Julien Gachdot, who translated all of the drawings from both editions of the books into p5.js sketches. He also got permission from Delahaye himself to share the scans of both of the books. I have included all of the project details as well as the links in the description box, so be sure to check it out. Today, we'll be focusing on just one sketch, specifically this one called Grid the Circle, which is from Chapter 9, Dessin Implicite. While Julien stays true to the structure and the syntax of the original piece, I'll actually be preserving the logic, but I'll be coding in my own personal style, which is something that feels natural to me and probably you too if you have been following my channel. The piece that we're going to create is going to be part translation, part remix, and overall a celebration of how playful and experimental creative coding can be. We'll start with the base code from the book / Julien's code, but then we'll do some experiments to see what kind of surprising results will emerge. Before we start coding, let's look at the base code just to see how it works. All right, I'm going to come down here first in setup. So as you can see here, it has a nested for loop. So we're going to be creating a grid of circles. And inside this nested loop, you can see that there's a function called calculf or calculate compute f and dessin circle. So this is to draw the circle. So dessin actually means drawing in French. Basically, we're going to be drawing a grid of circles, but what is interesting with this sketch is that in this calculate f function here, it has a bunch of if-else statements for each of the drawing, each of the dessin. So as you can see here, it has a number to 51, down to 266, and each one of these compute the value f differently. For example, what if we just click run? So this one is dessin 261, and you see we have this nice unique shape of 4 bigger circles, but it is created by a grid of smaller geometric shapes. And if I change it to, let's do 251, which is the first drawing, you can see that we have this pattern where the circles that are at the outermost corners have the biggest radius. So if you come down here to this line of code here, you can see that the equation is what? F equals to absolute value of x times absolute value of y. In this sketch here, the center, which is in the middle of the sketch, has a value x and y of 0, 0. And the range is from -1 to 1 on both x and y axis, which means that the circle that is at the corners has the biggest radius, right? The biggest distance from the center. So if I were to, let me comment this, and what if we say f equals to xx times yy? You can see that we now only have 2 sections of the drawings, right? And that is because in this first quadrant here, the x value is positive and the y value is also positive. No, the y value is negative. That means that there is some translation here which makes the multiplication here become positive, and then we see the drawing on the top right corner. And similarly, what we see on the left side here, the result from this multiplication is positive, and that's why we see the radius here. But in these 2 quadrants, you don't see anything, and that is because the multiplication results in a negative value, and so that negative value, once we translate into a radius, it's a negative radius, so you don't see anything. And that's why in this sketch, they put in absolute value to make sure that the result of this multiplication is positive. Another interesting thing about this sketch is that if you come up here, you see all of these values here, N and RR. Basically, it sets the number of rows and columns and also the size. Usually what we do in our sketch, or what I like to do, is that I set number of columns and number of rows, or the size, and then we calculate columns and rows by that, right? This is exactly what is happening here. So right now, N is 20. So I believe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are a total of 20 rows. So if we, how about we decrease this to 10? You can see that now we only have a 10 by 10 grid, right? And if I increase it to 50, then it's bigger and we have a different shape. So that is something that we can play around with. And they have all of this code up top here just to say that they want the number of columns and rows to be different for each of the drawings. And I'm not sure what RR is, but we can play around too. It's the reverse. I think this is the size of the radius, the maximum radius maybe. Yeah, you can see that the circles are bigger. All right, so that is one sketch. Another one that I want to look at, and it actually is the one that I will also be sketching later, is number 264. All right, it's here. So as you can see from the equations here, it's quite similar to the one that we just looked at, right? Which is a multiplication between x and y, but then now there's no absolute value, and also there is this constant of 50 in front of everything. So it seems like it's probably a scaling something. Actually, why don't we actually also just run it, right? 264. All right, so you can see that it's kind of like a tiling of some sort, right? Okay, so let's look at this first. So for 264, the n size is 120 and the radius is 1 over n. So if I do n size to be, let's do 20. All right, so it's a lot different, right? So if we do 50. All right, why don't we keep it there for now? Actually, let's keep it at 20. Maybe that might allow us to understand the code a little bit easier. So now let's come down to 264 here. We're not going to talk about this line of code yet, so I'm actually going to comment it out, and I'm going to just set f to be equals to this. So you should probably know what this is going to be like, right? So it's exactly what we did previously, right? But by multiplying with 50, we get a much larger value, and that's why the radius is just huge. But what makes that sketch look like a bunch of tiles is actually this line of code here. So if I do 1, all right, that creates a pretty interesting pattern. What if I put in 2 instead of 1 here? It looks like it creates 1 extra tile. So if we do 3, 1 more, 4, and if I do 10, it's a little bit incomprehensible now, but what I want to tell you is that the equation here, f equals to z minus floor of z, allows us to do this tiling trick. And how does it work? So let's look at this. The value of x and y is between -1 and 1, right? So when we multiply it, it will return value between 0 and 1. So if I were to put 1 here, it would just return value between 0 and 1. So z is between 0 and 1 minus floor z, and floor z basically gives us a value between 0 and 1 also. So we get a return value of f between 0 and 1. So it doesn't actually do anything when the constant here is 1. We get this pattern here. But if I do 2, so now when we do this calculation, z is actually a decimal number, right? And floor of z turns the value z into an integer. So when we subtract this, we get the fractional part of the value, right? And so now f ranges between 0 and 1 again, and that's why the size is between 0 and 1. So when the value of f hits an integer, it becomes 0 again. Similar to how we would usually use a mod function, right? A modulo function that does a division between two numbers and returns the remainder. And that's how we usually loop through stuff. This is a similar way to do that. But the reason that I want to use this like the way that they use it here is because it actually deals with negative numbers, unlike mod. But we'll play around in the next sketch just to see how the two methods would impact the sketch. Because we multiply this by 2, you can see that there are two sets of tiles, right? And if I do 10, you can't really see it here, but what if I change this back to 120? And if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the value 10 does something to the pattern here. It doesn't look like a tile based on how we color it here, but you can see that it looks like a tile here. There's like some boxes. Anyway, I just want you to understand the code a little bit before we start coding. So let's get to work. All right, so let's declare a few variables: columns, rows, and size. So instead of setting a specific number of columns and rows like the original sketch, I want to set the size. So that is basically the size of each of the cell. So how about we start with 20? And then we're going to calculate columns to be width divided by size and rows to be height divided by size. And then now in draw, we're going to be drawing a grid of circles, ellipses. So I'm going to use a nested for loop that goes from I equals to 0 to I less than columns, I plus plus. And then the inner loop will be j equals to 0 to j less than rows, and then j plus plus. And inside here, we're going to draw circles using an ellipse function. It takes in 4 arguments, the x and y coordinate of the center of the circles. And I'm going to put in x and y here. And I'm going to set x to be equals to I times size, and then y to be equals to j times size. And this is going to allow us to space the circles out evenly. And then we're going to put in the last 2 arguments, which are the radius, the diameter. So radius times 2. And how about we set radius to be equals to size divided by 2. All right, as you can see here, we have a grid of circles, but they're not offsetted correctly. And by how much that we need to move it to the right and down. It is actually by size divided by 2 for both x and y. Perfect. And then also inside setup, I want to put in no fill. Now we only have a grid of circles. What we want to do is that we want to differentiate the radius size, right? By computing the value f. How about we write a separate function, and I'm going to call it compute f. We're gonna put in, how about 2 parameters for now? I'm gonna set it as xx and yy. And the reason that I'm not using x and y is to make it clear that actually x and y here is the values between 0 and columns minus 1, which is based on the grid itself, right? The size of the sketch. But actually, xx and yy that we're going to put inside this function to compute is going to be between -1 and 1, right? So actually, let's do that first. So we're going to do xx to be equals to, we're going to map the value of x that goes between 0 and columns minus 1. We're going to map it to -1 and 1. Same thing for yy. Actually, no, it's not x and y. It is I and j, right? That goes from 0 to columns minus 1 and 0 to rows minus 1. Okay, then basically we just need to do, we need to set f to be equals to compute of xx and yy, which we're about to write here. So let's do the same equation as the DESSIN 251. Let f to be equals to absolute value of, actually, I want to try this real quick. So xx times yy, and then return f. And we're going to set r to be equals to, instead of a constant value of size divided by 2, it is going to be f, right? Okay, run. Nope, compute f. Huh, interesting. All of the 4 quadrants are filled. -1 and 1. So if I say if f is more than 0, then we set this. I just want to see. Let r. Okay. What I wanted to see is, because in the original piece, right, you can see that the 2 quadrants that were filled were the top right and the bottom left. But actually in computer graphics coordinates, the positive x and y is actually in the bottom right, and the negative x and y is actually on the top left. I just wanted to check. But apparently, if I don't put in this if statement, we get all 4. So I guess if the value of the radius is negative that we pass into as arguments in P5, it turns itself into positive value for us. Great. Or not great if you don't want that. But if you don't want it, you can use a conditional statement like what I just did. Okay, so as you can see, the radius size is quite small. So what I want to do is also, how about we put a value of max r. So let's do max r to be, what if we do 50? Pretty nice. Let's do a little bit smaller. Okay, so now we get the first sketch. So how about we play with the second one? So now inside compute f, I'm going to first set this as 251. Let's put it right on top. All right, so inside here, let's do let f, and if DESSIN is equals to 251, then we're gonna be computing this f here. This would just be f, and we need to put one additional parameter here, DESSIN. Okay, else if DESSIN is equals to 264, right? So now what we want to do is we're going to declare z, and then we're going to set z to be equals to, I'm going to actually set a variable. Actually, let's do tile num times xx times yy, right? And then let's just do tile num to be equals to 1 for now. And yes. And then f will be equals to what? Z minus floor z, right? Okay, and then we also need to change this to 264. Ellipse was expecting a number in the third parameter. Ah, okay. So we need to put in inside this compute function in the draw function here, DESSIN. Ta-da! All right. And then now if I change this to 10, okay, why don't we actually set the size, the max radius size here to be, I want it to be a third of the size. Okay, looks nice. Let's do 10. Nice. Okay, instead of no fill here, let's actually fill it with, yeah, just do black. Okay. Very basic, very simple. Good. And we can change the tiles num here to, let's do 20. All right, 50. And this is how you start to experiment. But then now I don't want just a static picture like this. I want it to be animating. So we're going to introduce another variable. Why don't we call it, actually we're basically going to be changing this tile num here, right? But I want it to also reflect in the 251 DESSIN 2. So let's just start with 251. Okay, and we're going to put in, what should be the variable name? How about zoom? Zoom. We're going to multiply it here. So basically, instead of a value between -1 and 1 for XX and YY, we now multiply it by zoom. And basically, we're going to start zoom at 0, and then we're going to do speed to be close to 1. And then in draw, we're going to increment zoom by speed. And let's see what happens. Zoom, we need to put zoom here too. You see something and then you don't see anything. And do you know why that is? It is because the size of the circle gets extra large after a while. Actually, it would be really cool if we do no fill. It might be cool. Let's see. It's pretty cool, huh? Okay. Wow. Look at that hypnotic piece. Wow, that looks cool. I did not expect that. But I guess when a bunch of circles are on top of each other, it creates this new, larger, unique pattern. Okay. We're good there, but let's go to 264. I'm going to use the same zoom variable here, but we're going to multiply it to this, right? This equation here. But as you can see, it's basically the same thing as tau num. If we keep tau num, I'm going to start at 1. So basically, there's only one tile, and then this zoom, as we animate, as the draw function is called, then we're going to have a bunch more tiles, and that should look nice. Let's do 264. Whoa. Okay, so I want to decrease the speed size, and I'm going to delete no fill here, and then let's just fill it with the color black. Okay, you can see that the tile patterns emerges here, right? Okay, but I think it's still a little bit too fast. Let's slow it down. Okay, I might be pushing it. Okay. All right. Actually, let's speed it up a little bit more. Play around with the speed that works for you. And then the last piece that I want to play with is the color. And I'm actually going to be using a new color mode called HSB, which stands for hue, saturation, and brightness. So basically, instead of RGB, which represents the color red, green, and blue, hue, saturation, and brightness looks at the hue color from this color wheel here that goes from red to red between the values of 0 to 360. And then saturation and brightness just give it the how bright and contrasty the color will be. And the range is between 0 and 100. So we need to put in setup here, color mode, HSB, and then we're going to put in 360, 100, and 100. I believe that if we don't put in this 360, 100, 100, it might still work. The default hue value might range between something else, not 0 to 360. You can check the documentation page. But if we do this, it is just to be safe. And then now inside here, instead of filling it with the color black, we're going to map the hue, and I'm going to map it between 0 and 1, and I want the hue color to be like bluish, so I'm going to do 120 to like 220, and then I want the saturation to be 80 and brightness to be at a full max 100, and then we just put in H is B here. All right, play. Nice. Okay, I also want no stroke. All right, and let's give it a little bit of a darker background, which is going to be this color here. All right, and remember when I was telling you about how we do detailing using the equation z minus floor z, which is similar to how we would use the modulo equation, right? But the difference is in the fact that it deals with negative numbers. So let's experiment with that too. If we come down here, instead of using this function, I'm going to do f equals to z mod 1. So actually, a number mod 1 would give the fractional part of the number 2. But with, let's just run. Look at that. Look at the color, right? With using this modulo function, modulo expression, it's a little bit different because it actually spits out a negative number of the fractional part, but if the value is negative, it gives a negative value too. And because I map this color ranges between 0 and 1, that's why you get a different color for the other sides here, which looks really nice. And how about actually instead of no stroke, I'm going to do stroke, and let's do HS and do, how about we do B to be equals to 50. I think it gives like a little bit of like a glowing effect. And the last thing that I want to do is, what if we increase the size of this canvas, and then, yeah, let's decrease the speed a little bit and give it the last run. That looks really nice. Okay, so this is my take on a recreation, retranslation, remix, whatever you call it, from the original piece by Delahaye, as well as the translation from Julian. I hope that you give this one a try because it's super fun and very creative and surprising. Give it a try.